All right, we're going to start this unit on what's called quadratic relations. And you'll notice we don't call it functions for a very important reason. Quadratic still means squared. Like when we were talking about quadratic functions, they were y equals x squared. Quadratic relations have things that are squared, but they're not functions. Another name for this would be conic sections, and we can talk about why they're called that at another time. But a quadratic relation has x squareds and y squareds both in it. The general form for a quadratic relation, and circles is just the first of the four main types we're going to talk about, is ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. I know that looks like a whole lot and it looks pretty complicated, but as we'll see as we move from one conic section to the next, it's not as bad as it seems. First of all, this b term is almost always going to be 0 xy. b will almost always be 0. And then what we have is an x squared term and an x term, a y squared term and a y term, and a constant term. So the values of a, b, c, d, e, and f will determine what kind of conic section, what shape it is, and also the features of that conic section, or the features of that graph. And we're going to start today with circles, and those are what happens when a equals c. Okay, so in our big quadratic relation equation, if a and c are the same, then the result is going to be a circle. And this big equation will make more and more sense the more of them we'll see, but let's just start with some basic circle talk today. So first of all, here is the equation of a circle that's centered at the origin. X squared plus y squared equals 16. This is an example of a circle whose center is the origin and whose radius is 4. Okay, so in general, x squared plus y squared equals r squared is a circle centered at 0, 0. So if you want to draw it, the middle of this circle is just the origin, and the radius of 4 takes it out to 4 in all directions, so it's going to go through 0, negative 4, negative 4, 0, and all combinations of that, and we just draw a circle in. I have to do a little drawing this unit, so just do the best you can. And this is the equation of the circle that is represented with x squared plus y squared equals 16. Now, I said earlier these are called quadratic relations, not quadratic functions, because you'll notice this thing fails the vertical line test. There are more than one y value for a given x value. And so a lot of these shapes are going to fail the vertical line test, so we can't call them functions anymore. All right, but this is a quadratic relation. The reason that it fails the vertical line test is because now y is being squared too. If you just have y equals and then some x squared and x terms on the right, it will pass the vertical line test, but now it fails it because both of them are squared. And this is our first example of a circle. Let's move on to a little bit more complicated. Okay, the general form of a circle that doesn't have to be centered at the origin. X minus h squared plus y minus k squared equals r squared. So all we're doing is taking a circle like we had on the last screen and shifting it left or right, up or down. We're still going to have the r squared value on the right, but the center of this is hk, and the radius is r. Now we still, like I said, we already knew the radius was r, but this center being hk. Now there's a built-in negative in the formula. So what that means for us is our shifts are going to be the opposite of the sign that we see. For example, x minus 4 squared plus y plus 3 squared equals 25. So you need to be able to look at this equation and find the center and the radius. And that's really all there is to a circle. You know, you only need 2 points to draw a straight line. You only need a center and a radius to draw a circle. So the center is 4, negative 3. That's what I meant by the built-in negative. It's the opposite of this and the opposite of this. So let's just go to 4, -3 and make a dot. And then let's use the radius, which is 5, all right, the square root of 25. Sometimes that's a nice, neat number. It doesn't have to be, because the radius could be any number. Ours happens to be a whole number 5. I'm going to go, the easiest way to draw these is to go 5 in all directions. 1, 2, 3, 4, 5. And then just, once you get those dots in place, your circle, even if you're not the most artistic, your circle will be all right if it goes through those 4 spots. Okay, so that's how you draw a circle given the equation. No big deal. A lot of our time this unit's going to be spent turning something that looks like this into a form that we can graph. Now I know this is a circle because the coefficients of x squared and y squared are the same, and I talked about that on the first slide. I have 1x squared plus 1y squared. When that changes, we have a different shaped graph. But as long as those are the same, it's a circle. So I need to manipulate this equation because just looking at it the way it is, I don't know the center and I don't know the radius. So let me find the standard form for a circle and then graph it. When we did vertex form of parabolas a long time ago, we completed the square. We're going to do 2 completing the squares on the left side of this equation. So watch how I'm just rearranging. I'm moving the 6 to the right, and I'm grouping the x squared with the 4x and the y squared with the -6y, and I'm leaving 2 blanks there that I'm going to use to fill in and complete the square. If you remember completing the square, we take half of this 4 and square it, and we get a 4, but we can't add 4 to one side without adding 4 to the other side. And then we take half of this -6, which is -3, we square it and get 9, and I need to add 9 to the other side to balance that out. So writing this thing with the 2 completed squares, x plus 2 quantity squared plus y minus 3 quantity squared equals 6 plus 4 plus 9, which is 19. So the first thing I notice is that 19 is not a perfect square number, but it still has a square root, and that's going to be the radius of our circle. So this circle is centered at -2, +3. And my circle is going to be drawn right through the middle of my work here, but that's all right. -2, +3. My center is here. And my radius is the square root of 19, which is, let me check that on my calculator. Square root of 19, could get it ballpark, but it is 4.3588. Let's call it, let's just call it 4.4. So if I go 4.4 in all directions, 1, 2, 3, 4, and not quite half, down 1, 2, 3, 4, and 0.4, 1, 2, 3, 4.4, and up 1, 2, 3, 4. So sorry again for my picture ending up right in my work. That's what I get for trying to do my work on a grid. But there is the equation. All right, center, -2, 3, radius, square root of 19, or about 4.4. So this one, two main features of this. We have to manipulate it to make it look like the standard form by completing the square, and not every single one is going to have a nice, neat radius. The center could also be not at a nice, neat point. This one, neat center, not neat radius. That's all right. It happens. Okay, and then one last twist is, what if I asked you to write the equation and I gave you a picture, or I could just give you information about the circle. So if I say write the equation of that, remember we're trying to fill in x minus h squared plus y minus k squared equals r squared. I can see that my radius is 3, so that's going to make r squared equal to 9. My center is -5, -3. So the x-coordinate's -5, and since that built-in opposite is a part of it, I need x plus 5 squared plus y plus 3 squared equals 9. If you can graph one given the equation, you should be able to backtrack and write the equation given the graph without too much more added trouble. And the last thing I want to talk about is just the definition of a circle. You know, my 4-year-old son knows what a circle looks like. We all know what circles look like. We know what they are, but sometimes the definition is a little bit more technical. A definition of a circle is all points equidistant from a fixed point. If you think about it, to get that perfectly round shape, it's like if you ever seen in somebody's backyard, they let their dog out, but they put him on a chain in the backyard where they put a stake in the ground, and then the dog has, let's say, 15 feet to run around because they're stuck to that chain. So they can be outside and they can run, but they can't get any more than 15 feet away from that chain. So here's my dog. If my dog is in the backyard, they're going to run in all directions possible. So what gets traced out is a perfect circle, perfect to some degree, because the dog is going 15 feet out in all directions. That's all points that are the same distance away from that fixed point. The chain is fixed in the ground. All of these points that the dog is tracing are 15 feet away from it. So what gets created is a somewhat perfect circle, but it's a good illustration of what the definition is. So if you have to define a circle, all points equidistant from a fixed point.